So we are going to talk in this tutorial about the classification method and some logistic stuff that we want to remind you that everything is on everything of the course is in the website or in the Moodle. This is a 4 credit point course. We're going to have 2 hours to lecture per week. And in the tutorial, we also cover new material. So it's not like going back over what you have learned in the lecture. So please count as the tutorial as mandatory as well. We're gonna have 4 homework assignments. The first one is already out, so please check that out. And all the communication is through Moodle, but as I started to say, you can feel free to approach us if you see us or at the end of the lectures or something like that. So another thing I wanted to say is that feel free if you have questions during the tutorial. Don't wait until the end. Please ask during. You can raise your hand and I'll be glad to help you because I want you to understand what I'm teaching you. So in the first lecture of ASAF, we started to cover supervised learning, and the main idea of the supervised learning that you're given a set of data sets where xi are, I'm sorry, I don't know why it's doing like this. Maybe I will change the 1 second. And just hold on. Okay. So xi are the data points and yi are the supervision. This is the values that is corresponding that someone gave us that is corresponding to the xi data sample. And the two, 1 second, I have another one. Okay. It's not working now. Okay. And the two main categories that we have for supervised learning is depending on the supervision label itself. When we're talking about regression, we're talking about where the yi's, where the labels or the values that are corresponding to the data are some continuous values. So for example, here we have that xi is the values on the x-axis and yi are the values, and you learned how you can maybe fit some linear predictor that is as close to the generalized data as close as possible. And the second option is classification. So here the xi's are these data points, and the labels are going to be the class which these data points are belong to. So we have 2 classes in this case. Some of the data points are belonging to the green classes, and so the other one is belong to the red one. And the goal here is to predict, to learn some classifier which distinguish between the two. Another thing that I wanted to maybe point it out at the beginning is that during the talk, I'm going to say some words that are not maybe on this screen, like classifier, predictor, learning optimizer. It's like some words that are the same, but people will use that also during these talks, and you will soon gonna use that yourself while you're going and diving into machine learning and deep learning. So even if it's not like maybe on the screen, just like I'm gonna give you some synonym of the words that people are using in the techniques in the fields. So a few examples, like because we are talking about computer vision, of course, this is our goal. So the data points are usually going to be images. So tests for regression can be image denoising. So the input to the problem is going to be a noisy image, and we want to regress to the denoised version, to the clean version of this image. This is what we want to predict. And another one is object localization. We're given an image, yet again as the input, and we want to regress maybe the boundaries of where the objects lies in. Classification, maybe it's more straightforward. We're given an image when we just want to know what is this class of this image, whether it's a cat, whether it's a dog, and this is our goal in computer vision most of the time when we're talking about classification. So you covered regression in the last lecture, and now we're going to talk about the classification, a bit of theoretical and also some technical aspects of this. So we're going to start from binary classification, and when I'm saying binary, we only have two options for the class. Say, for example, I get this new email and I want to classify whether it is a spam or not a spam. So I have only two options, binary 0, 1, negative or positive, to distinguish between. So here, for example, this is a spam. So to be more maybe formal, as before, as I said, we have a set of samples. Xi is some vector in dimension d, and yi is the label, and because it's binary, it can be either 0 or 1. So let's say, for example, like the email spam detector, we are given the text email, maybe it's embedded into some feature vector, and this is our data xi, and we want to classify whether it's a spam, whether it's 1 or not a spam, 0. So we're given a data set of size m, which can be of any size. We don't know what the size of it. And we want to learn some hypothesis, some predictor or classifier that, given a new sample, will classify for us whether this new data is 0 or 1. And we also parameterize that by theta. Theta can be whatever, and we will see a specific case of some hypothesis with parameters with some data in this class. So the most simple and first classifier that we're going to see is the linear classifier. And here theta is composed of two components, which is W are the weights and B is the bias. And our hypothesis is just like given a new sample and applying a linear transformation with W and B. And one here denoted as the indicator function. And we are asking whether this is a positive or a negative, meaning this does this new point is above or beyond this linear classifier. So let's see some simple example. Let's imagine that our data point is from dimension 2. So W will be of the dimension 1 times D. It's going to be a vector of size D. This the same as the data point dimension. And B is a simple number. And if we can point it out on maybe on the 2D plane, so imagine we have some positive values which have the label of 1, and we have some negative examples which have the corresponding supervision label of 0. And this is, for example, some linear classifier, right? So W is going to just be the normal of this linear, and B is the bias, the distance from the origin. And another important notion is the decision boundary. This is the boundary where the classifier distinguishes between where it goes from classifying a point in space, here in this example on the 2D plane, as 1 or as 2. Okay? Okay. So given this description of the hypothesis and with parameterization of WB, how can we find a good parameters for this linear classifier? And another thing that is very important is how can we interpret the results, right? Something that we want, I think, for the rest of the course is to somehow explain to ourselves what this linear predictor linear predictor or classifier is giving us. So, for example, if for one example x1, the result of the linear classifier is 1000, okay, we know for sure it's classified as 1. What if the result is 0.6? Like it is a bit. So if we're gonna put this again on the 2D plane, we can see that like it kind of resembles the fact that we have a point that is kind of close to the decision boundary, and far away from the decision boundary. And maybe our predictor is not really sure or certain about the data sample X2, but for X1 is like it knows for sure that it can classify that as one. So we need some measurement or some intuition to say, okay, what's going to be a good classifier that is certain about our data points. Even if we will see maybe options in the part of the course, how can we even measure that? But currently we're just like talking intuition-wise, what we want to do. Because from the intuition, we maybe want to push further X2 from the decision boundary, so it will be more certain. So in order to get some intuitive or interpretable classifier, we're gonna take one step ahead and slightly change our linear classifier to something that is called logistic regression. Don't be mistaken by the word regression. It is still a classification method that we're talking about, and you will soon in the next slide you understand why this word regression is coming from here, but it's still classification. So using logistic regression, we're gonna get I'm not sure why I'm having trouble with this word, but interpretable results. The decision boundary will still be linear, which is again intuitive and nice to see. And there is an easy way to find WUD. So we have everything as we want. So first of all, let's get some intuition of why this classifier is good and how can we interpret it. So how we're gonna change this linear classifier, we're gonna add some logistic regression, logistic function on top of the linear prediction. So instead of looking at just like the linear transformation y-x plus b, we want to give this the intuition of looking at it as a probability. So it will give us some interpretation of what is the result, like how the result is gonna get. So instead of just like doing the linear transformation, we're gonna apply a sigmoid of it, and sigmoid is the function is usually denoted as sigma, and it is 1/1 plus exponent of minus z, when z here is the output of the linear transformation. And it looks somewhat like this, like exactly like this. So if you can see already from this drawing that it transforms every point to lie between the range of 0 and 1. And this is something that is close to be a probability because we have something that is between 0 and 1. And now we change our prediction. Instead of just like being greater or lower than 0, we want it to be greater than half. And the interpretation is that the output of the logistic regression classifier is the probability of having classified the point xi as 1. So the corresponding label yi is exactly 1. And if you can note it, again, if we're just like looking at the negative opposite the probability, 1 minus the sigmoid, we want it to be the probability of having labeled our data point as 0. Okay, so we have this this logistic regression classifier using the sigmoid, and we have this probability interpretation. And the idea and the main intuition is that we want to predict the highest probability event. Yes?
Is the probability real in any?
Is it what?
Is it a real probability in any like quantitative sense, or is it just nice to think about it?
It is also nice. Maybe it can also can be seen as probability once you will see how we can maybe train it and use it. But it is a real probability in the sense that you have some data distribution. You can think of the data set distribution as well as some data measurement, right? You sample some data points and you predict what is the probability of having classified that as one. So there is some randomness here that you can exactly think of it as probability.
Okay, but it's not like if I test all the samples that have 0.99 as a result, the 99 will be accurate and one will be false.
It depends on the data points. Like if you have maybe infinite data, then maybe it is true. But yeah, because usually you only have like a subset of the data that you're examining this. Okay, so wait, sorry. So we have in mind the interpretation of thinking about this as probability, and now we want to see that we're still gonna maintain the nice property that our decision boundary is linear. This is quite straightforward. As we recall, this is our hypothesis, our predictor, and we have that we're gonna have like the indicator function gonna say one, like we classify that as one, if and only if we have that the sigmoid of z is greater than half, and this is only happens if z is greater than half. You can see that also in this plot here from the right. And as you recall, z is the linear transformation using y and b of our data point x. And again, we're gonna have a linear decision boundary. So given some y and b, it's still gonna look as like a 2D line or a plane in d dimension, where the d is like the dimension over there. And the last one, which will be kind of like the focus of our talk, and you started to look at it with Asaf, is how can we find a good W and B? How can we learn it? How can we optimize for that? So I'm going to give you the main points where we need to do, and we will go over each one of them. So the first thing is we want to define a convex cost function, or a loss. This is another term that we will refer to it as. And first of all, what do I mean by convex function? So, when I say convex function, the first thing that came in mind for me is, it's just like a U-shaped or a bowl-shaped kind of function. And convex functions are usually good for that. You know that each point that you start on this function, if you go like down the hill, just like throw this ball down, you will gonna reach the global minima of the function. So you see, for example, here, this is non-convex. You will not reach the global minima of the function, and it's not a U-shape. So this is like there is like a formal mathematical description, but like just like think of you, this is they may be a bit more easy. And the idea of the loss function is that we want to penalize some errors. Like we want to penalize the predictor and want to inspect how good our classifier is. And what this means is that if our classifier predicts a wrong prediction, we're gonna have large penalty that is approaching to infinity. And if our classifier predicts correctly, we want that the loss or the cost function will approach to 0. And we're gonna use gradient descent to update WB using the loss. You slightly, I think, covered gradient descent in the last lecture, but we're gonna see a concrete example in the next few slides. So let's start by define a specific cost function, and we'll see how it is exactly penalize the errors of the prediction as we want. So the specific loss that we are going to talk about is the cross-entropy loss. And the cross-entropy loss is given a prediction. From now on, we're going to denote that prediction as WI hat. So usually hat is like for the prediction, the WI is going to be our label.
Said WI.
YI, sorry. Exactly. Thank you. YI hat, and YI is going to be the label, the ground truth label that we have in mind. And this is the cross-entropy loss. Don't be afraid maybe of this long question. It's not that it's very interpretable and intuitive. So if our yi is one, is classified as one, we have only the first term, which is log of minus log of the prediction. So we want to actually you can think of it that we want to maximize the probability of predicting yi, because we want it to reach to 1. And if our yi is classified as 0, we have only the second term, and here we want to push the prediction into 0. We're going to see that maybe more concrete, and just note that yi is either 0 or 1, and the prediction is lie between 0 to 1. And again, think of like probability in mind. So we want to ask ourselves, is that a good cost function as we said? So let's see what I roughly described, maybe more concrete. So assuming that the label is 0 and our prediction is approaching to 1, as I said, we have only the next term, right? Because the first one is canceled out. We have a log of 1 minus something that is approaching to 0. So we are approaching to, our cost function is approaching to 0. If our classifier predicts something that is approaching to 1, we have something that is approaching to minus log of 0, which is approaching to infinity. So you see that if we have a good prediction, we're approaching to 0. If we have bad prediction, we're approaching to very high cost function. And this is, again, true for if we are classifying that as 1. Okay. So this is our cross-entropy loss. And it is good because, first of all, it is convex, just like it's basically a log. So you can think of it as U-shape is not going down with respect to W and B. And it is, as we saw, penalizes for the wrong predictions, and it is 0 for the correct predictions. So some intuition behind cross-entropy, and maybe this will also relate to our interpretation of looking at the prediction as probability. So the term entropy is coming from information theory, and it kind of measures the uncertainty of our probability. What do I mean by uncertain? When I am saying uncertain, I mean that all events have the same possibility. Like we don't know on Monday Asaf can come in every shirt, like in every color of the shirt. We don't know like all the events, all the shirt colors are possible for this event to happen. And when do I mean by certain is that I have only one event that is possible. I know that Mark Zuckerberg will always wear gray shirt all the time. So I'm certain this is gonna be the event that is going to occur. And if we write this formally, given a probability measure P, the entropy of this probability is going to be the sum over all the events, minus the sum of all the events, the probability of this event, and log of P of X, log of the probability. And another way to interpret the entropy is that we're calling it as like it is the expected number of bits in order we want to represent an event. Okay, so think of like when we are certain we have only one event that is possible, we don't need many bits in order to describe it. And the relation to bits is like if you are recalling that if you have log of some number, it's going to define how many bits you need in order to describe that. Also think of you can also think of if you have certain, so you don't need many bits in order to represent all the events that is possible. And if you're uncertain, you maybe need more bits in order to represent all the possible events that you have. We are talking about cost entropy. is when we don't look at only one probability measurement, is that we have a Q of X, which is an approximation of our desired probability. So from now on, you can think of P of X as our ground truth label, ground truth probability, and Q is our predictor, our approximator of that probability. And how many bits do we need now? Like, how do you measure the bits that is required in order to represent the events? We use Q as the representation, so we're gonna plug in Q inside of the log, because Q is the one that we're using in order to represent these events. So it changes to be minus the sum over all the possible events, the probability of this, and the log of the approximator Q of X. And of course, it is a minimal function when we are exactly approximating Q using P. So back to our setting. Let's see how can we define P and Q in our setting. Again, our goal is to learn some prediction, learn some W and B, such that the sigmoid of this linear transformation gonna give us the prediction yi hat, which, as you recall, is this is what we're gonna denote as our approximator. This is probability of a given xi. We classify that as 1, and we want it to be as close as possible as the ground truth probability, which is P of yi. And another thing that we noted, we saw that before, if we're looking at the negative probability, like 1 minus the probability of having that it's classified as 1, is just like 1 minus the prediction yi hat. Okay, so given the training, like when you're training, we're given a data set, we know the label, we know the yi. So the probability of yi to be 1 given xi is just like simply gonna be yi. Okay, it's gonna be 1. If it's classified as 1, it's gonna be 0 if it's classified as 0. And accordingly, the probability of it's classified as 0, it's going to be y minus, because if you see, if yi is 0, the probability is 1. If yi is 1, the probability is 0. Okay, finally, we defined P and Q, and we want to plug in to the cross-entropy formula, the desired P and Q. And this is exactly what we described and showed you before as the cross-entropy loss. So we have minus the sum over all the probability of either having classified this function as 1 or 0, multiplied by our prediction, minus log of the prediction of this classification.
You just change the problem on the way, right? Because
what do you mean?
The first, you know, the problem of that your ground truth was just probability 1 being 1 plus.
Mhm.
Now you said that I think P is also a ground truth,
Yeah,
and now P is also a probability. So
yeah, you're
that-
gonna, this is kind of like the interpretation of that, right? This is exactly why we call it logistic regression, because we're thinking of like we are regressing to probability. But underneath, we just like have 2 options, right? We just like have yi either 1 or 0. So it is slightly a change of the problem, but eventually we are classifying our predictor is predicting some classification. It predicts either it's 0 or 1, and that's it. Did I answer your question?
But the ground truth is also telling us what is the labels are.
Yeah, the label are still 1 or 0, right? But you can think of it, given 1 or 0, the probability of having 1 is just like, you can think of it like it is 1 if it's classified as 1, and 0 if it's classified as 0. It's pretty simple, like probability. And this is exactly our loss. Okay. So, okay, we described some convex cost function, which is the cross-entropy loss. We saw that it is penalized error for us. It is convex. It's good for us and for what we will be there to do. And now we want to see how can we use a gradient descent in order to update and find good W and P. So let's start from the single example. We are given only one data point, which is xi, it's a vector in RD, and yi is either 0 or 1. First of all, what we're going to do is we're going to find a prediction. We're going to apply the linear transformation using some W and B that we initialized in a random way. And we're going to apply a sigmoid over it. So we're going to have a prediction yi hat, which is going to be the probability of having either 1 or 0, and it is lying between 0 and 1. Second thing, we're going to calculate the loss. We're going to just compute the loss that we introduced before, the cross-entropy loss. And now we want to update the weights. So given some initial weights, we're going to apply a gradient descent step. So we're going to find the gradient over the loss according to W, and we're going to go into the direction of the gradient, which is going to give us the steepest descent direction in order to minimize our function, our loss, because our goal is to find the global minimum of the function. And if you recall, if we're going to take some steps according to the gradient, we're going to reach the global minima and basically minimize our loss. Similarly, we're going to update the bias. I didn't went over the derivation of the specific loss. I think, I'm not sure if you can go over that yourself at home. It's basically just like derivation and calculus. But as you can see, both of the gradients are pretty simple and easy to compute. And an important notion that we have for gradient descent is this parameter here that you see alpha, and this is going to be our learning rate or our step size that we're going to take into the direction of the gradient, because I think one of the most important parameter in deep learning exists, because because we are talking here in this example only on a single example, but our loss is eventually we're going to think of it as computed over all of our data. So taking only one example is going to just give us an approximation of this loss, and taking a direction might lead to, like, it's going to lead to the minimum of the function, but only for according to one example. So we might diverge if we're going to take large step size. So usually people are taking like small step size because it is an approximation of our expected loss. Okay. I think that in the previous slide, previous lecture, we talked about full batch gradient descent. But if not, I will say it like again, like if you have a bunch of data, ideally what we want to do is to compute the loss for all of the data, but most of the time it's intractable. You can have like million or billions of data points in your branches label. So people are doing what is called stochastic gradient descent, or SGD in short. Wait, sorry. I think I have disconnected or something. Okay. So what we're gonna do in stochastic gradient descent, we are gonna sample random set of M examples, which we call a batch or a mini batch. So a set of M examples, which are the data points xi and yi are the labels. We're gonna compute the loss for each pair, for each one of the data points and the prediction for it. and then we're gonna take the loss as the average or the expected current mini pitch loss. And then instead of updating only for one example, we're gonna update the loss and differentiate it according to all of these data points. And possibly we're gonna get maybe a better approximation of the loss, and not only for one example. And the same, we're gonna update the bias B. Okay, so if we're back to supervised learning and kind of like building all together as some high-level blocks, what we usually have in supervised learning is that we have some training data, training data set that is composed of the data points and their parameters labels, and we have some algorithm like learning or optimization algorithm, and the result of given some learning algorithm and the training set is our hypothesis, which is our predictor or classifier when we're talking about classification, or regression when we're talking about regression. And what we've seen is that also the learning algorithm is composed of three factors. First of all, we need to define the hypothesis class. What is the class of the classifier that we are interested in? What is the loss, the cost function that we want to minimize? And what is the optimization method that we're gonna use? So when we're talking about logistic regression, our hypothesis class is gonna be the linear transformation applied with a sigmoid function after that. So our parameters that we are searching for are W and B. The loss is gonna be the cross-entropy loss, and the optimization method is gonna be SPD. There are a bunch more of optimization method that we're gonna see later on in this course. Okay, so just to summarize logistic regression. First of all, I said it a bit before, the wording for regression coming from the fact that we are doing like probability regression, okay, but it is a classification after all, just like maybe a nicer way to interpret that. It is a binary classification. We're talking either 0, 1, negative or positive examples. We have a linear transformation, a linear decision boundary. And we are using sigmoid in order to get some intuition of the result of being a probability height output. And we want to predict the highest probability event that is occurring. Either the highest probability event, is it given a new data? Is it classified as spam or not spam, dog or cat or whatever? And in order to learn this linear classification, we're gonna use the cross-entropy loss, which is convex and penalized for mistakes. And we're gonna apply gradient descent or stochastic gradient descent in order to update the weights and the bias. I think maybe before moving on to the multi-class classification, we can take some 10 minutes breaks, okay? So be back. Okay, so in the first section, we talked about binary classification when we only had like 2 options of the class. What if we're going back to this spam detection, what if we have another option? Maybe you're not sure if we want another option of maybe it's a spam, so we can go over it. So it won't throw it up into the spam folder. But again, this is actually a spam. If we're talking about vision input, so in image input, usually we don't have only cats or dogs. We have many animals. What if you want to expect which animals is the image is describing? So let's make it again more formally. We have C classes, and now our data point is as again a vector in RD, but now instead of having only 0 and 1 options for the label, we have it between 0 to C. Okay, so C is going to be like the index is going to be to which class this data point is belonging to. Here we have, for example, the email spam example. So it can be 0, 1, or 2, where 2 state for the maybe class. And as before, we have the training set as a set of xi, yi. Y are the labels for xi. And we want to predict a hypothesis, where before we wanted to predict one number, which was between 0 and 1. Here we want to predict to which class. It's not going to be either 0 or 1. It's going to be which class this data point is belonging to. And as before, we parameterize the hypothesis, the classifier, by theta. And we're going to slightly change the logistic regression classifier into something that we called a softmax classifier, which is the generalization of the logistic regression from a binary classifier to multi-class classifier. But the idea and the intuition behind is exactly the same. So as before, we begin with some linear transformation, where again, W and B are gonna be our learnable parameters, and we apply some nonlinearity to this linear transformation in order to transform Z to the prediction. And yes, again, we're gonna think of it as probability. And for the final decision, we want to pick the event that has the highest probability to occur. Like, given some new data, what is the highest probability that this data point is a dog? And so there are slightly changes in how do we generalize. So in the logistic regression, we had W as a vector because we wanted only to predict one value, because here we want to predict C values, like the probability or the score for each one of the classes. W is the weight is now in matrix, which is dimension big C, the number of classes times the dimension, and B is a vector in R3. And we can think of it as a score, as I say. So Zi, the output, is going to be the score for the, I'm sorry, not I, the J. The Jth input, like entry of this vector, is going to be the score for the Jth class. Okay. And we don't want to look only on the number of the linear transformation. We yet again want to transfer this, like to apply some nonlinearity in order to look at it as a probability between 0 to 1. So if for the logistic regression we use the sigmoid, we're gonna introduce a new function which is called the softmax in the next slide. And the softmax is gonna give us some nonlinear transformation that from scores, we're gonna get like a probability interpretation of the Jth entry of Y hat is gonna be the Jth probability of this class. And now we're given a vector of a probability, and instead of we don't have only one value, so we cannot just distinguish whether this is greater or equal than half. We just want to take the what is the class that has the highest probability. So we're going to take the argmax of these probability vectors. And the learning and the optimization is just gonna be similar to what we saw before. We're gonna apply the cross-entropy loss. It will be a slightly change because we're gonna have multiple classes now and multiple probability for each one, and we're gonna apply SGD in order to update the weight and the bias. So let's start from examining some simple example. We are given a text xi of some email, and the possible labels are not spam for 0, spam 1, and maybe for 2. So let's say that our vector, our input is from dimension 4. This is the input, and this is, for example, the weight that we are initialized or we're training now learning. So we're just gonna do matrix and vector multiplication and add a bias for that. And this will result with the linear transform version Z with these values. And the first thing we want to do is to apply an exponent to these values. And the softmax function is basically applying an exponent to each one of the values, and then normalize according to all of the entries. So this will give us a result for each entry to lie between 0 and 1, and it will sum also to 1 if we're summing all these probabilities. This is the y hat that we're having, y I hat for this thing. So again, interpreted as probability. So again, only interpretation, intuition. We can think of it. Okay, the prediction said it is 93% this is a spam, 2% it's not a spam, 5% maybe a spam. And again, in terms of the intuition, we think of y I hat as a probability distribution, and the J entry is the prediction probability that the class is belonging to J. I want to maybe clarify something that was talking that you asked. I think the guy from the back that's in the next the past section. It is just like an interpretation of probability. It's not really a probability. It's just like the output of the linear classifier. Okay. So let's make this a bit more formal. We converting that into some probability distribution over some classes. We're gonna apply the linear transformation, and we have the output of the linear transformation is a vector of scores in RC, and then the softmax function is applying exponent to each one of the entries and normalize that. And our prediction y hat is applying that for each one of the entries of the scores. And so each one is the probability of the Jade entry, Jade class, and it sums into 1. Okay, so we have this generalization from logistic regression into softmax using the softmax function that switched from the sigmoid. And now we want to see how we're gonna learn this kind of function. Again, similarly to as we did before, using the cross-entropy loss and the SGD. And let's start from cross-entropy loss and let's see how it looks for the multi-class example. So if we write down again the cross-entropy and how it looks like, just to remind, it's the minus of the sum of all the event, the ground truth probability, and the log of the approximator. And here, the probability the ground truth is no. This is probability that that xi is classified as the C class, and the prediction is the output of the softmax classification, and this is what we denote as Q. So the upscript of C is going to be the C entry of the prediction I. Of the prediction, y I hat. Okay, this is our prediction, our probability prediction for the C class. And as we saw before from the examples, we have from the right, this is the prediction, the 2%, 93%, and 5%. And from the left, we are noting what the probability of the ground is going to look like. So another term that people are referring to this type of vectors is like one-hot vector. So we have only one, and where it is classified as not a spam. So let's say, for example, that this data point xi as ground truth label of that the label that is classified to is 1. So it will be only 1 in the first, like 1 entry, if I'm counting it as like 0, 1, 2. And in the other entries, it's going to be 0. And if we plug in P and Q that we defined into that cross entropy, we're gonna again sum over all the possible events, and eventually everything is gonna be zero out because we have a probability of 1 only for the correct class that is classified, and it's gonna be minus log of the prediction of the C class. Okay, for here it's like the 1 entry. And our goal is to make the prediction to be closer to the contours, right? So here, as you can see from this log, we want that 93% will be approaching to like 0.393 will be approaching to 1. Kind of like resemble this probability to be close. In general speaking, not for these only 3 options example, we have a training example, xi, and L is the index of the class which this data point is belonging to. And we are computing the loss. It's going to be sum of all the events of the probability. And again, we say that the probability is going to be 1 only for the class which this data point is given or supervised for us that we know it is belonging to. So it will be exactly the L entry. So we only left with minus log of the prediction at the L entry. Because we said it's only going to be 1 there. If we're going to plug in what is exactly why I had this entry, it's going to be, we're just going to put in the softmax function, going to be the exponent of this score of this class divided by the sum of all of the scores. And if we can think that we want to minimize this loss, in another way, we want to make the argument instead of the log to be larger, to be approaching to 1 exactly. And there are 2 ways in order to do that. One way is to increase the numerator, increase the score for the L class, make it high confidence, like I'm sure this is the class for sure, whatever. And another way is to decrease the score for all of the other class that, like, I know it is, it's not like I know it's a dog, I know it's not a cat. So this is how the cross-entropy for the multiclass looks like. And now in the next slide, we're going to see some example of how can we apply SGD for this loss. So if we put the gradient descent algorithm that we stated before for the logistic regression part, let's see how does it change when we have multiple class. So first of all, as we saw before, we have a change of the label. It's not either 0 or 1. It can be from 0 to C minus 1. Like we have C options for that, big C options. In order to find the prediction, we again apply a linear transformation, but instead of applying a sigma, we apply the softmax function and have a prediction be a vector in our big C. Which is the probability of the, each entry is the probability of the J class, and it's summed to 1. We compute the cross-entropy loss for this class, and yet again, we are updating the weights and the bias. So here we see some, it is like the generalized option, the general option of having multiple class and not only 1, and we can see the difference in the gradient. Again, we're not going over the derivative, but see this notion of delta function is going to be 1 only if yi is classified as C, okay, and it's going to be 0 otherwise. So yet again, it's like the 1 hot vector that we're thinking about in mind, that we're comparing only the score of the I'm sorry, the probability prediction of the C class. Yes.
How do you get 1 multi-vector? You have vector of distributions. If you want to get the 1, you take like that one.
No, so think of like the ground truth, right? You're given, let's say you have the three option, I don't know, let's say pro option, you know, that this image, you're given a data point xi, an image, and, you know, it is belonging to the second class, okay? And you have four options. So the ground truth, one hot vector is basically gonna be a vector of length 4. This is the only option, and it's gonna be one only in the second class, because this is the ground truth class.
You are only talking about training?
Hmm?
You're only talking about the training?
Yeah, in the training, it is, yeah, I'm just talking about the training about yi. This is the one hot vector. This is the supervision. And I think you will see that after that, but in order to inspect in the prediction, you're gonna take the argmax of the probability. So let's say you have, like we saw before, like 0.93, we're gonna take 1 as our classification prediction. But while we're training, we're gonna think of it like we saw before, like regression for probability.
There's
Yes.
no sense about being less wrong, right?
What do you mean?
It's either, for example, I don't know, I see a cat and I can confuse it with a dog, but I don't confuse it with a fish. But in here, if you see, for example, a dog, and you're not 100% sure it's a dog, there's no like price that you pay for choosing fish instead of cat.
I'm not sure I understand the question again.
You're maximizing the probability of choosing the right one, but you don't really care about the other probabilities.
No, but we saw it before, right? We saw that there are two ways in order to, wait, it's not here, where was it? Show it like this.
Of course, but you don't care which of them is side.
Here. If you look at it like this is the prediction, right? In order to make it, it's not just like in order to make the loss lower. You only can make the confidence of this is a cut higher. You can only also decrease the confidence about other, like saying it's not a dog, okay, and by that you can minimize the loss.
Yes, but you don't really care about the relative size of the other ones, right?
Yeah, we don't care.
Just you care about choosing the right one, and
Yeah.
the wrong ones you want to make them as
Yeah.
like as small as possible.
Yeah, generally speaking, if you're talking about like cross-entropy loss, it has this attribute of pushing the decision boundary quite far away. Because we're using exponent and log, it's gonna push for having high confidence, which is good and bad. Maybe you're gonna see that later in the course, but that is like generally speaking.
This would be the opposite. It would decrease the loss more to be just as not confident that it's a fish and a dog
Yeah,
because it's exponential.
yes. This is one of the attributes that cross-entropy loss usually have. That it's make the predictor to be pretty high confidence. Maybe sometimes it's not good. Wait, where were we? Okay, so let's go back to the building blocks of supervised learning, and let's see how the softmax classifier lie into that blocks. Again, we have the training data, the learning algorithm, and some hypothesis, which is the result of the optimization process. And we need to define the hypothesis class, the loss, and the optimization method. And the only thing that basically changed here from the logistic regression is that now we have a different hypothesis class because we're gonna use an argmax of the softmax of this linear transformation instead of just like predicting whether it is the output of the sigmoid is greater or lower than 0. This is maybe answering your question about there. How do we inspect in test time? Okay, so to conclude, we talked about two options of doing classification, either when we have binary classification and only have possible of 2 class, then we're gonna use logistic regression. Or if we have multiple class, then we're gonna talk about then we're gonna use the softmax classifier. But in each way, we're gonna have we need to learn some weight and bias, which gonna be notions that will be accompany for us all of the next lectures. And we're gonna use and we're gonna use learning using some loss function. Here we showed you the cross-entropy loss. We're gonna see much more options for the losses in as the course continue, and SGD, which is basically the basic of what people are doing with deep learning. Some practical things that we need to consider, and maybe you will be encountered with your first homework, is first of all, how can we compute efficiently on mini batches, and some numerical stability issues that we can encounter in the fact we're going to use a computer with some numerical approximation ability. So let's go back to this algorithm of SGD. So we sampling a mini batch, and then the tricky part is calculating the loss for each one of the pair. So if we're gonna do in this section, we're gonna do like a for loop of calculating the loss for each one of the examples. It's gonna be heavy if we want that the batch it's large or it is computationally heavy. So we want to make this much more efficient. And the way we do that is using linear algebra, basically. And the fact that we can do matrix multiplication quickly, and using the GPU, it is even quicker. So just to remind you, this is how the computation look for one example. We have xi as a vector, and then we do like a matrix and vector multiplication, then sum, and all of this thing. This is for only computation, only for how we compute the prediction, only for one example. What if we have a batch example, and we can just examine how it looks for only a batch of 2 examples. I don't know, let's say the first one is classified as not a spam, the second one is classified as a spam. And what we're gonna do is simply pile the samples into a matrix, where each row is the sample, is one of the sample. And we're gonna use the transport version of W and do matrix multiplication. And the result of that will be a matrix of size 2, which is like the number of the examples times the output of the vector, so times C. So note that we want to add this to a vector only of length C. So one of the things that you will maybe encounter now in the homework, that is something that is called a broadcasting. Okay, so when you sum like a matrix that is 2 by C with a vector which is only type C, it's gonna think of it as like repeating the vector of C as the size of the matrix. So it's just like adding B in each one of the rows. Something that is maybe not intuitive at the start, but something that will be more intuitive as you will practice more of with PyTorch and some matrix manipulations. So the result, as I said, is a matrix of size 2 by C, the score of each one of them. And then we're going to apply exponent to each one of the entries. And again, we're going to normalize across the row, because we don't want to mix between the different examples, right? So we're going to only normalize according to the first example, and then we're going to normalize the second row according to the second row. Again, something that is very intuitive, will be very intuitive to you, and will be easy to define in PyTorch later. And this will give us the metric of the matrix of the prediction. So the first row is for the prediction for the first example, and second as well. And here we see again the one hot vector. So because the first example is labeled as 0, it's going to be one hot vector when we have one only on the 0 axis, on the 0 entry, sorry. And for the second one is a one hot vector, which is one only in the first, in the one entry. Okay, and then we simply can apply the cross-entropy loss between these two matrices. So basically, the main thing that works for deep learning is make it pile up and make the utilization of metrics manipulation like in order to make it more efficient and fast. Let's just go over it quickly of how can we make it formal. We define the data matrix or the sample matrix as the piling up of all of the examples, which is a matrix, as I said, M by D. D is the dimension, and M is the number of the size of the batch that we are using. And again, we are like similarly, we're going to look at big Y to be the ground truth label metric, where each row is going to be the one hot vector corresponding to the classification of the ith example. And W is going to be the weight is going to be matrix C, big C times D. B is vector RC. We're going to apply method multiplication, which result in a matrix of size M by C. And again, we're going to use broadcasting in order to add B to each one of the rows. And this will result in like applying this linear transformation, we're going to get the score matrix, which is a matrix of size M times big C. And we're going to apply a softmax and the cross-entropy loss to each one of the rows. And once we have the cross-entropy for each samples, we simply can compute the average loss using all the losses that we computed. And as well as the computation, we also going to apply the gradient descent, the updating of the weight and the bias using some metrics form. So here, this is what we saw before of how we can update the weight only for one example. But we can also use that as mini batch. So it's similarly derived as we saw before. We can think of like updating just like taking one update and piling up this result. And instead of the delta I, we can see here explicitly the one hot vector matrix that we are comparing with the prediction. Another note that is important to understand is about numerical stability. And so there is some precision in most of the GPUs and the things that you're using. I think the default is like 32 bits. There is a trend now that everybody is working with even 16 bits precision because it works faster and you can train deep learning neural networks faster like this. But it can be some burden sometimes. If you think of cross-entropy loss or using softmax, like if you're gonna have in softmax, you're gonna have the exponent, and it can be extremely large. And if it is like larger than the precision of that you're using, it can be nan out or infinite, and basically it's not fun. Right? Because even though we are normalizing, if we have some infinite value according to the computer into the precision of the computer, we can have like a problem with this stability of our computation. And another thing that we are using cross-entropy and we are logging something that we don't know what is the value of this thing will be. Like, let's say I initialize the weight and the bias in a way that yi hat is close to 0, right? We don't know what it's going to be. So if I'm logging that, I'm going to get minus infinite. I'm going to that none's in my computation or infinite, and again, not fun. There are some possible solutions, like easy things that you consider. Let's, for example, what people are usually doing in the second option, like if you have log of something and you're not sure if this value can be 0, you just add a small number to it. So like very, very small, e to the -5, in order to not NaN out, and it's like not really affecting the learning. And actually that's it. We cannot, I think, finish before the time. Usually tutorial is gonna be a bit more fast, I think. But if you have any questions, or something that you want to further ask or understand, please feel free.